All right, let's dive in. Today we're tackling string theory. You've provided us with Brian Greene's The Elegant Universe and some pretty intense scientific papers.
Sounds like a fun challenge.
We're going to break it all down so you get the big picture without getting lost in the complexities.
Definitely. It's great you brought the elegant universe. It actually connects to something Einstein was thinking about, a unified field theory.
Ah, Einstein. Always ahead of his time.
He really was. He was looking for one theory that could explain all the forces in the universe.
Wait, hold on. So we've got gravity, electromagnetism, the strong and weak forces. Are you saying there could be a single explanation for all of them?
That was Einstein's dream. It's still alive today, and string theory is one of the leading contenders. It's a candidate for what physicists call a theory of everything, or TOE.
A TOE, like a theory that explains everything. That's a pretty big goal.
It is. Finding a TOE wouldn't mean we've solved all of science, but it would give us, like, the ultimate foundation, the source code of the universe.
Okay, I like that. The source code. So it's like everything's woven from the same thread, but incredibly complex. And string theory says that thread is, what, tiny strings?
Exactly. Tiny vibrating strings.
But what about atoms? And all those particles inside atoms, I thought those were the fundamental building blocks.
Oh, our understanding of matter has evolved over time. I mean, we started with the ancient Greeks who thought atoms were the smallest things.
Right, indivisible.
Then we discovered that atoms were made of even smaller things, protons, neutrons, electrons.
And even those are made of quarks.
Exactly. And what string theory proposes is that all these particles, like electrons and quarks, they're not actually point-like. They're tiny one-dimensional strings.
So instead of tiny balls, we've got little vibrating things.
Yeah, think of them like incredibly small, vibrating rubber bands.
Okay, how do those little rubber bands make up everything we see? I mean, it's a big leap.
Well, think of a violin. Different vibrations of the strings create different notes, right?
Yeah.
In string theory, it's the same idea. Different vibrations of these tiny strings give rise to the different particles and forces we observe. One vibration could be an electron, another a quark, another a photon, which makes up light.
So everything we see, from atoms to galaxies, it's like a giant string symphony.
In a way, yes. And this idea actually helps to resolve some big problems in physics. Like, there's a fundamental conflict between Einstein's theories of relativity and what we know from quantum mechanics.
Brian Greene talks about that conflict. Can you remind me about relativity? I'm a bit rusty.
Sure. So there are actually two theories of relativity, special relativity and general relativity.
Okay.
Special relativity completely revolutionized how we think about space and time. It showed that time isn't absolute, it's relative.
Relative.
It means
What?
time can actually pass differently for different observers depending on how they're moving.
Hold on, you're saying time isn't constant, like it can speed up or slow down?
Yeah. And the speed of light is constant for everyone, no matter how fast they're moving themselves.
This leads to mind-bending things like time dilation.
Time dilation, what's that?
It means time actually slows down for objects that are moving very fast, close to the speed of light.
Is that a real thing or just a theory?
It's real. It's been measured. Think about those tiny particles called muons. They're created high in the atmosphere and have a very short lifespan. But when they travel at nearly the speed of light, they live longer from our perspective because their time is slowed down. It's as if they're tiny time travelers.
Wow, okay, I can see why this is a deep dive. But you said there were two theories of relativity. What about the other one, general relativity?
Ah, yes. General relativity is Einstein's theory of gravity.
Oh, right, gravity.
It's the idea that gravity isn't really a force pulling things together. Instead, it's the curvature of space-time caused by mass and energy.
The curvature of space-time.
Yeah. Imagine a bowling ball on a rubber sheet. Makes a dip, right?
Massive objects do the same thing to space-time. They create these dents that make other objects move along curved paths. That's gravity.
So things aren't being pulled, they're following the curves made by other objects. It's a completely different way of thinking about it.
It is, and it explains a lot of things. But here's the problem. When we try to combine general relativity with quantum mechanics, things get messy.
You said there was a conflict. What's going on there?
Right. Quantum mechanics is the theory that describes the universe at incredibly small scales, at the level of atoms and subatomic particles.
Right. And things get really weird at that level.
You do. One of the key principles of quantum mechanics is that energy comes in discrete packets. It's quantized.
Quantized.
Like, imagine money. You can have $1, $2, but you can't have half a cent. Energy is like that. It comes in specific amounts, these little bundles of energy.
Okay, that makes sense. But how does that conflict with relativity?
Well, things in the quantum world, like light and electrons, they don't just act like particles. They can also act like waves.
Like waves in the ocean?
Not exactly, but they exhibit wave-like behavior. Light, for example, is both a wave and a particle. It can behave like a stream of photons, but it also creates interference patterns, like waves overlapping.
So it's both.
Yeah, it's strange,
Yeah.
but it's what we observe. And then there's this famous experiment called the double-slit
Well,
experiment.
I've heard of that one. That's where they shoot electrons through two slits and they create this interference pattern.
Exactly. It's as if each electron is going through both slits at the same time, interfering with itself. That wouldn't happen if it was just a tiny ball.
It's like it's in two places at once.
That's the mystery. It's like saying you could travel to the store by taking every possible route at the same time, even through walls.
My head is spinning. But it's fascinating. Okay, so where does the conflict with relativity come in?
When we try to describe gravity at the super tiny scale where quantum mechanics rules, Einstein's theory of general relativity breaks down. It gives us nonsensical answers, like infinite energies.
So we need a theory that can handle both gravity and the weirdness of quantum mechanics.
Yes, and that's where string theory comes in. It's the leading candidate to unify these two seemingly incompatible theories.
Okay, back to the strings. How do they solve this problem?
String theory avoids these infinities because unlike point-like particles, strings are extended objects. They have a length, even if it's incredibly tiny.
So their size matters.
It does. Because of their size, strings smooth out the quantum fluctuations of space-time. That prevents the appearance of those catastrophic infinities.
So they're like cosmic ironing boards getting rid of the wrinkles in space-time.
Huh. That's one way to think about it. And this leads to one of the most mind-boggling ideas in string theory, the need for extra dimensions.
Wait, extra dimensions? Like beyond the three we experience?
You got it. String theory requires extra spatial dimensions beyond the up, down, left, right, forward, back that we're familiar with. But don't worry, we can't see them directly.
How can there be whole dimensions we don't see?
Think of a garden hose. From far away, it looks like a line. But up close, you see it's round, it has a circumference.
Okay.
String theory says that extra dimensions are curled up, kind of like the circumference of that hose. They're so small that we don't notice them.
So we could be living in a universe with, like, 10 dimensions or something.
Maybe even more.
This is getting deep. All right, I'm officially mind blown. Extra dimensions, tiny strings making up everything. This is a lot to take in.
It is, but it gets even more interesting.
Oh boy, I can't wait. Okay, I think I'm starting to wrap my head around those extra dimensions in these tiny strings. But Brian Greene also mentioned something called supersymmetry. What's that about?
Supersymmetry is a fascinating idea. It predicts that for every known particle, there's a partner particle, a superpartner.
A superpartner. Like for an electron, there's a super electron.
You got it. Well, not exactly super electron, but you get the idea. Each particle would have this partner with related properties, but a different spin.
Spin? You mean like the particle spinning around?
It's more of a quantum property. We can't really picture particles spinning like tops. What matters is that supersymmetry predicts these partner particles, and physicists are actually searching for them at the Large Hadron Collider.
Oh, wow. So finding them would be a big deal for string theory.
Absolutely. It would be major evidence supporting supersymmetry and the whole idea of string theory.
You mentioned earlier that there are actually 5 different versions of string theory. 5? That seems like a lot, doesn't it?
It did seem messy for a while, but then physicists realized that these different versions are all connected through something called dualities.
Duality.
Think of it like having 5 different maps of the same city. They might look different, use different symbols, but they all describe the same underlying place.
So the 5 string theories, they're just different ways of looking at the same underlying reality.
Exactly. And these dualities lead to some pretty mind-bending insights. There's this one called the large-small radius duality. It says that if you have a dimension that's curled up really small, the physics is the same as if it were incredibly large.
Wait, what? So a tiny circle is the same as a giant circle? How can that be?
It's one of the strange consequences of these dualities, but it actually hints at something important. There's likely a minimum size for these curled up dimensions.
A minimum size, like a limit to how small they can be.
Right. And it ties back to that idea we discussed earlier about how strings smooth out space-time. They prevent us from probing distances Smaller than the Planck length.
Planck length, that's a new one.
The Planck length is the smallest possible distance that has meaning in physics. It's unbelievably tiny, about 10 to the power of minus 25 meters.
Okay, that's tiny. So we've got 5 string theories connected by these bizarre dualities, a minimum length scale. How are we supposed to make sense of it all?
Well, that's where M theory comes in.
M theory. What's that?
It attempts to unify all 5 string theories into a single framework, suggesting they're all just different aspects of an even deeper, more fundamental theory.
So M theory is like the ultimate theory.
It might be. We're still trying to understand it. It's pretty mysterious.
Mysterious. Even the name is mysterious. What does the M stand for anyway?
No one knows for sure. Mystery, magic, membrane. Maybe you can come up with your own interpretation.
Maybe I will. But speaking of mysteries, how do we test any of this? You said these strings are way too small to see directly.
True. That's one of the big challenges. But there are some potential ways to look for indirect evidence.
Like what?
One way is to search for those superpartner particles. The ones predicted by supersymmetry. If we find them, that would be huge.
And where would we look for them?
In giant particle accelerators,
Yeah.
like the Large Hadron Collider, smashing particles together at incredibly high energies and seeing what comes out.
Okay, that makes sense. But what about looking for evidence in space?
We can do that too. The early universe, right after the Big Bang, was incredibly hot and dense. The energies were off the charts. String theory effects might have been much stronger back then. We might be able to see some hints of those effects in the cosmic microwave background radiation.
That's the afterglow of the Big Bang, right? We're looking for echoes of string theory from the beginning of time.
Exactly. It's pretty amazing when you think about it.
It is. Any other places we could look?
We could also search for clues in gravitational waves, those ripples in space-time that were predicted by Einstein. They might carry information about the very early universe, a time when string theory effects could have been important.
It's incredible to think that these tiny strings could have left such a big mark on the universe. Before we move on, you mentioned black holes earlier. What does string theory tell us about them?
Black holes are really interesting in the context of string theory. They push our understanding to the limits. String theory can help us understand things like black hole entropy and the information paradox.
Black hole entropy.
Entropy is a measure of disorder. Turns out a black hole's entropy is connected to the area of its event horizon.
The event horizon. That's the point of no return, right?
Yes. Right. Nothing, not even light, can escape from inside the event horizon. What's cool is that string theory can actually explain why a black hole's entropy is proportional to this area.
Wow, so string theory explains that connection. That's pretty impressive.
It is. But there's this other puzzle, the information paradox. It asks, what happens to the information that falls into a black hole?
Well, if nothing can escape, wouldn't that information be lost forever?
According to classical physics, yes. But quantum mechanics tells us that information can never be truly destroyed.
So there's a conflict again.
Right. String theory suggests a possible solution. It proposes that the information falling into a black hole isn't destroyed, it gets encoded on the event horizon.
Encoded, like a secret code.
In a way, yeah. And as the black hole slowly evaporates.
Wait, black holes evaporate?
They do. Stephen Hawking showed that. It's incredibly slow, but they do eventually disappear. And as they do, the information that was encoded on the event horizon might slowly be released back into the universe.
So it's not lost, just scrambled and spread out. That's crazy.
It is crazy. But it shows how string theory can tackle some of the most fundamental questions in physics. Questions about black holes, information, and the nature of reality itself.
This is a lot to take in. From tiny vibrating strings to the mysteries of black holes, this deep dive has been a wild ride so far. What else is there? We've talked about so much already, from tiny strings vibrating to these mind-boggling black holes. But there's one more big idea I gotta ask about, the multiverse. Greene talks about it in The Elegant Universe. Is our universe just one of many?
Ah, the multiverse. It's a question that's captured the imaginations of physicists and, well, everyone really. And string theory adds a whole new layer to it, literally. With all those possible shapes for the extra dimensions, some string theorists think there could be countless other universes out there, each one with its own unique set of physical laws.
So like a cosmic bubble bath of universes, all different.
That's one way to picture it. Each universe would have its own kind of tune played by those vibrating strings, leading to different constants of nature, maybe even different particles and forces.
It's almost too much to imagine. But it makes me wonder, if there are infinite universes out there, with every possible set of laws. How can we ever know anything for sure about our universe? Doesn't it make it all seem kind of random?
That's a great question and a real challenge. But there are ideas that try to address that. One is the anthropic principle.
The anthropic precedent.
Yeah, it basically says that we observe the universe we do because it's the kind of universe that allows for observers like us to exist.
So we see this universe because it's the one where we could see it. That seems a bit circular, doesn't it?
I know it can sound that way, but think of it like this. If the constants of nature were even slightly different, stars might not form, or atoms might not be stable. Life as we know it wouldn't exist. We wouldn't be here to ask these questions if the universe weren't set up in a way that allows for us to be here.
Okay, so the multiverse, this idea of all these different universes, and the anthropic principle kind of go together to explain why our universe seems so fine-tuned for life.
It's one possibility, but it's not the only idea out there. Some physicists have proposed things like cosmological natural selection.
Natural selection, like
Yeah.
Darwin's theory, but for universes.
Exactly. The idea is that universes might reproduce, in a way, through black holes. Each new universe would have slightly different laws.
Yeah.
And the ones that are better at creating more black holes would kind of have more offspring.
So it's like survival of the fittest for universes. The ones good at making black holes win the cosmic lottery.
Yeah, it's a wild concept, but it just shows how string theory pushes us to think about the universe in these completely new ways.
This whole deep dive has been amazing. We went from tiny strings to a whole multiverse of possibilities. It makes you wonder what's next for physics.
String theory is definitely still a work in progress. It's a young theory, relatively speaking, and there are many challenges ahead. But it's already had a huge impact on how we think about the universe. It's given us this glimpse into a deeper reality where gravity and quantum mechanics might finally merge, where extra dimensions might be hidden just beyond our perception, and where our universe might be just one among countless others.
It really makes you realize how much we still don't know. It's humbling, but exciting at the same time.
It really is. Whether string theory ultimately turns out to be the theory of everything is still an open question. But the search for this theory, this deep desire to understand the universe at its most fundamental level, it's already led to so many incredible discoveries. And who knows what amazing breakthroughs are yet to come.
Well, I know I've got a lot to think about after this. If our reality is built on a symphony of vibrating strings, as Brian Greene suggests, who knows what other secrets the universe holds? Thanks for taking this deep dive into string theory with us. It's been a truly incredible journey.